You walk like that?
What?
Like what? My friend can like walk on his knees like that.
Alright, so I have an object here. That's exciting. Can I get into this circle a little bit? Sorry. Alright, so we're just going to play a game. It's going to be fun.
Oh,
Okay.
can we turn it on?
In a minute. Let's just continue to play the game as we are. Just give it a push. Like, hopefully we'll try to keep it on the ground.
I thought it was fictional. Yeah.
So, is this game fun or not so fun?
Not fun.
I like it.
It's alright.
It's like hockey.
But it's kind of like what you expect, right?
Yeah.
Yeah, it's not so exciting. Okay, we are one of the things that we're going to do is we want to switch into a mode where we can start to really observe this scientifically and talk about it, but we'll wait for a second for that. Okay, so I have this switch, right, and every switch needs to be turned. And then let's play our game again.
Yeah. There's less friction. It's like eyes
Yeah, so let's make sure everybody gets the touch. Alright.
I didn't
Huh.
get it.
Oh, you didn't get a touch?
Yeah. That's so cool. Yeah, I was never good at slime.
Okay. So this time we're going to play again. The first time was just the awe of the thing. So the next time we're going to really try to observe. Okay? And the first thing I want us observing is to try to come up with some, explanation of how it's moving. Like, can we describe how this object moves? Okay? So another round of the game. And just pass it around. So if people are watching how the object moves. Oscar.
Physics is fun.
Alright. Back to me. That's alright. Okay. How are we observing its motion? Sean.
Well, it slides across the floor more easily when it's on, maybe because.
Well, I don't want an explanation just yet. You're leaping ahead. Like, I just would like to say how it moves. Like, how would you describe its motion? Smooth. What other? We've got physics terms. We don't need like smooth. We can use our physics words.
Frictionless?
I don't think we studied a whole unit.
Less friction.
Constant what?
Velocity.
Velocity. You sure?
Not always.
So it kind of decreased a little bit.
So when people hit it, let's see. So if it's sliding from like me to Michelle,
And this is a different velocity.
that's a different velocity. But when it's moving across, when it's in the middle of between me and Michelle, how is it moving? How sure are you of that? Not entirely. Like, what would it take to convince you? Are you at the point where you're like, it looks constant velocity, I'm pretty sure? Or are you like, I don't even believe that it's constant velocity?
Like pretty sure, but we should measure the same.
What would you want to measure to do this? Could we do the breadcrumb method with this?
The meters thing.
I don't see why not.
No, it's too.
Go get some masking tape. Just imagine that I'm going to send you to get Oscar some masking tape and have you try to put masking tape down as this thing passes by.
I mean, if we like have a different distance and then we push it like a little slower.
Oh, okay. So if I were to kind of do this,
That did look constant.
that looks a little less constant. Okay, that's an interesting thing, right?
It looks pretty good.
Okay. Do you think the breadcrumb method can work with this?
It would just be easy.
It'd be very difficult.
It would be difficult. In theory, it could, but you'd have to be like you'd have to be a varsity breadcrumb dropper, right? Like, we can't have any of this like amateur thirds. You gotta step up.
I'm sorry.
So maybe there's another way to do this, and maybe there's another question like, maybe it's seeming constant here, but is it constant, over bigger distances? Does that seem like are people kind of convinced or wondering? Okay, so maybe we should go to bigger distances. What's the bigger distance that we're gonna go to?
Hallway.
Hallway, but we're gonna do two things. We're gonna close the doors of the classrooms, and we're gonna be quiet in the hallway so that people don't know we're out there with something as exciting as that. Okay? All right. And we're gonna one more thing. Can somebody take the camera, and we're gonna just kind of, you're gonna be kind of filming what we're doing.
The whole thing? Just
Yeah.
Wait, the tripod or the camera?
Probably the camera will lift out of the tripod. There's a little switch on the side. You see that pulls forward and the camera pops out. I'll get it in 1 second.
Oh, here we go.
It should just lift straight out if you lift that switch. Yeah, there you go. So now you're just going to film us. It should be running on and running. Can you guys pull the classroom doors closed?
Oh.
Yeah. Not that you can do that. Okay, I need one other person to do something for me. Cindy, why don't you be in charge of this? Okay, so this is also a camera, and so it acts like it's going to record stuff. It works exactly like an iPod does. Like you're going to record, you're going to sit here in the hallway, and you're going to see this thing kind of come across. Your job is just going to be to record it as it passes by, and you probably need to be on ground level. So let's get some people over here and some people over there. Oscar, why don't you take this and we'll do the first.
Where should I be, Mr. Burke?
What? You just want to be able to film so that we can see its motion. So maybe, Sophia, we can have you over here to start.
Where do you want me to start?
Yeah, you're going to start it.
Like right here?
Yeah. Is it recording?
Cool.
It's like curling. You don't think it's I think it is.
It is.
Oh, I'm not
Okay.
Pretty tough.
Like, is it faster to do that?
Let's send it back. You're going to have to give it a decent push to get it down.
I don't think so.
Cindy, are you filming?
Am I supposed to be filming here?
Yeah, start filming now because it's going to pass by you and I don't want you to miss it.
Look at my soccer tricks.
Okay, couple passes back. One more run down the hall. One more time, Andrew. Let's send it one more.
Let's send it slowly.
Yeah, it travels like 3 tiles per second. So you can maybe
Just leave it like going. Can we get it one more time this way? Because I think we missed it on the video. Alfonso, can you stop it and send it this way?
Cindy, do you want to use this one?
You taped it, but then it disappeared.
That's okay. I actually want it on the iPad. One more time.
No, but I know how to use the iPad camera if you're having trouble with it.
Shouldn't be filming. Ready? Was it in the frame this time? It's not? Okay, let's come on back in and turn that off. And Sophia, you can just put the camera back in. Ah, yeah. Where's the remote? Someone see the remote for the question.
So could we theoretically take that film and see where the speed was going at?
Yeah, so TJ asked a great question. Let the projector come on. So I have a movie of this object, right? That was just filmed with the iPad by Cindy. Okay? And now how could I use this video to verify whether or not it was moving in constant velocity? Cindy got a small part of the whole motion. But that's probably a good, chunk. It was like when it was passing the hallway. What would I know if I was looking at this film that would tell me whether or not it was moving with constant velocity? Can you describe how that would look and what I would need to do?
How many tiles?
How many tiles what? Per
Like,
second, like now I don't know per second, like what's a movie made up of anyway?
frames.
Frames. and each frame is what?
A certain amount of time long.
A certain amount of time. It's like a photograph. So if I take the first frame and then I look at the next frame,
And the distance between.
and then yeah, essentially on the line, like how many tiles it moved. And then I look at the third frame. What am I looking for? What's my check to see if it's constant velocity?
The same distance.
Same distance. Okay. And the awesome thing about this software, and if I can just make technology all work together, is like we're trying to get this to work where the Apple TV can project it, but it may not, and I may have to quickly abandon this.
Looks like
There we go. I think this is gonna work. No, not yet. No, I do not want to update now. Dang it, read the remote. That's the biggest one. Okay. So you can ignore while I'm dealing with this. So let's talk about forces while I'm trying to make the Apple TV work. Why don't you tell me some of the forces using our description that are acting on the puck? Like I noticed at some point from when Mr. Burke brought the puck out to where now when it's put away, these forces were acting on it. Tell me a force that was acting on it. Go ahead, Chris.
the force exerted when someone pushes.
You got to use our template now, because we're trying to practice describing it with this template.
The contact normal force of the.
So you're talking about like when I just push my hand into it,
Right.
contact normal force of the
hand on the
puck. Why did you say normal force?
because the normal force is it's the crunch atoms. So
Yeah, absolutely. So atoms in my hand were crunching right as they touched the puck. Okay, here's our video. Yes. So video physics. Maybe video physics doesn't play nice, but here. That's good to know. Yeah. It's too bad. So this is just okay. So the force of the hand. What's another force that somebody saw? Go ahead, Michelle.
The non-contact gravitational force on the soccer ball. On the soccer ball that exerts force on the floor.
Okay, so the non-contact gravitational force of the what? On the what?
Force on the soccer ball
On the soccer ball by the.
by the floor. I
It's
mean,
the-
not by the floor.
What was that? So I'm just going to start to write the descriptions down here. The first one that we had that we said we all agreed on was the contact, normal force of the hand on the ball. Okay, or puck. Let's it is. Okay, and Michelle is trying to say the non-contact
Gravitational force there.
gravitational force of what?
There.
the Earth.
Oh, right.
On the puck. Okay, Alfonso, did you have a force?
Yeah. Would there be the contact normal force, the air from the hovering puck exerts on the floor of the building?
Okay, is that acting on the puck? One of the things I want to kind of restrict ourselves to is forces acting on the puck. Okay, because I could talk about like the force that you're exerting on the floor and stuff, but that probably isn't going to get us to the
I think he means the air coming out of
Yeah,
the
the air coming out of the puck.
air coming out of the puck. So the puck is pushing air downwards.
I'm lifting.
Yeah, how is it lifting itself? What's pushing on the puck though?
Yeah.
The air. So instead of saying the non-contact force of the air on the floor, that force is really on the puck. Maybe one or two more and then we'll start to think about kind of making a diagram. How about when the puck is just like this, and where is the puck? Sophia, go ahead.
The contact force of friction, or the contact frictional force of the puck on the floor. Or the floor.
Of the
Floor on the puck.
floor on the puck. Okay. So flip into the first page of your packet. Like if you open to the next page, there's space for notes. And what we're going to try to do is put together a series of diagrams to help us explain what's going on. Have we established that the puck is moving at constant velocity?
No.
No. Are we at the point where it's close? Like if I could have brought video physics up and filled it frame to frame, what do you think that would have looked like?
Constant.
Pretty close. All right. I think it good enough for now. But it was only moving at constant velocity. When was sometime when it wasn't moving at constant velocity? When it was still, okay, we'll take that as a possibility. Like when it's just sitting here, this is not constant velocity. Agree, disagree?
Agreed.
Agree? All around?
Well, disagree.
Disagree, why?
Enough. Well, can it have a constant velocity of 0?
What do we think?
Agreed.
Yeah, I think agree, right? Because the other thing to kind of think about is really, I could begin to say, well, the Earth is moving, right? And so this velocity isn't 0 if I went somewhere else. But whatever its velocity is, it's not what? Changing. Yeah. So I think that velocity is constant right now. When was the time when its velocity wasn't constant?
When the fan wasn't on.
When the fan wasn't on and, because the fan's not on right now,
Oh, and it was being pushed.
and it was being pushed, you know, or when it was moving across the floor with the fan not on, that was the time when it wasn't constant. What was another time when it wasn't constant?
It was accelerating.
Okay, well, we don't have that word yet. Give me an instant of something that you see as acceleration that its velocity wasn't constant.
When we first pushed it.
Yeah, so while you were actually pushing on it, how did you know its velocity wasn't constant?
Because we went from 0 up to.
Yeah, it changed from kind of 0 to moving. Okay. Any other times that we saw that the velocity might not have been constant? I think that does it for now. Okay, let's first consider this moment. Puck not on. Okay, velocity equals 0, and it's constant. And the first thing I want to kind of talk about is making a special kind of diagram that I'm going to call a system schema. Okay? And basically what this is a way of listing all the objects that are interacting with the object in question. So the first thing I do is I just draw a circle and I put the puck inside of it. And then I think, what are all the objects that are interacting with this puck when it's sitting on the floor? Okay, Michelle?
Gravity.
Is gravity an object interacting?
Oh, no.
What's the object?
So, the floor?
The floor would be one object that's interacting with it. Okay, so I just draw a line to connect them that they're interacting. And what is the name of the force and the symbol for it that is the puck floor interaction right now when it's just sitting there? How would you describe that force the floor is exerting on the puck?
Non-contact.
It's a contact or non-contact? I think you're thinking about a different force. Contact normal force of the floor on the puck. So I can just write F sub n here to indicate that's the normal force. Agreed? Okay. What's the other object that's interacting with the puck when it's sitting on the floor? The Earth. How would I describe that interaction?
The non-contact gravitational force of Earth on the.
Sweet. Anything else interacting with the puck right now? Any other objects in the room interacting with the puck when it's sitting right on the floor in the middle of the floor? I can think of one possible object.
The air pressure.
Maybe air. Okay. So I'm wondering, do I need to have the air interacting? We probably need to discuss this out. Okay. Here's a demo and show. So Chris, here's this innocent looking piece of plastic. Pick it up, please. Okay, sweet. Now give it back to me. Here's this innocent looking piece of plastic. DJ, pick it up, please. Makes it a lot harder. Okay, sweet. Innocent piece of plastic, right? Pick that up, no problem. There you go, Michelle. Pick it up, please. Oh my God.
Move to the edge of the table.
Right? Innocent piece of plastic. But same piece of plastic, hasn't
Move to the
changed
edge of
at
the
all.
table.
It's the air push.
What changed? What's the difference between the piece of plastic when it's like this?
Suctioning.
So is there suction that suddenly just develops? And is a suction an object? How are we gonna just, we have to kind of start to break down what's
There's
happening.
a lack of air underneath.
Okay, so underneath, right now, is there air underneath the?
Yeah.
Yes. Okay, just like there's air under the table, air. When I push this down, what happens?
There's air, more air. It's pushed.
Yeah, most air is pushed out. All? No. There's, if I went down there like, and I actually tried to count all the air molecules that were underneath the piece of plastic, how would I be able to do it?
No.
No. Like it's still an incountably, impossibly huge number, but it's way, way fewer than that case. Okay? So no air, let's say no, very little air underneath the piece of plastic. Is there air above the piece of plastic?
Yes.
Yes. Okay. And is there air under the table?
Yeah.
Yeah. And the air that's kind of above the table, what's it kind of, and it's above the plastic, what's it doing to the plastic?
Is it trying to get like under the plastic?
It might be, but let's just for a moment say that it can't. So it's hitting the top of the plastic, right? Like air molecules are hitting and bouncing off.
Pushing.
And what are they doing under the table?
Pushing. Up.
Hitting and bouncing off, right? But in between, that's not able to happen. So what's that doing to the piece of plastic and the table?
It's pushing them together.
It's pushing them together. So that when I suddenly am lifting up, right? If this is a big enough piece of plastic, the air could be holding them together. I have a bigger piece of plastic somewhere that I can actually lift the table pretty nicely. But if all I do is I press this little black knob,
Oh.
what happened there, Andrew?
The air molecules came out.
The air molecules come rushing underneath, and then when I lift up, the air molecules are pushing on top and they're pushing on bottom. No big deal, right? Huh. So what's going on with the puck? Is the air interacting with the puck in a way that I want to be worried about? I mean, like right now, I definitely have to be concerned. Like this air would be interacting if I was making a thing for the cup. Right now, is air interacting with it? In a way, like the total interaction of the air here is 0. And we can say, right, it doesn't matter. What about the pump when it's on? Yes or no?
When it's on.
Cindy, you say when it's off. It's right like this. Air significant or not? No. Because right now, is there air underneath here?
Yes.
Yeah. Okay. So no air.
But when it's on.
But when it's on, we'll get to that in just a second. Okay? So how many interactions are there acting on my pod? How many forces are acting on my puck now? Two. And so that leads me, so this was the system schema. That's just kind of a way of thinking about what forces are acting on the object. That leads me right into the next diagram we're going to draw a lot of, and that's called a free body diagram. We call it a free body diagram because we imagine the puck is just a little dot and we're freeing it from everything else in our minds. And we're going to draw the forces as arrows in the directions that they're acting. So Michelle's force that she named, the gravitational force of the Earth, which way does that point? Down. Okay? And I can label that force carefully. I can say it's the gravitational force of the Earth on the puck. You see my notation, the way it works? Earth, arrow, puck. That's helpful. It's a nice little check to kind of make sure it saves me from having to write a complete sentence for every force. But in my mind, I'm still saying that sentence. What's the other force?
The upwards force.
Yeah, the upward force. So that's Fn. What are the subscripts?
Floor.
Floor, arrow, puck. Okay. think about those two forces, how they compare in size?
They should be about equal.
Probably about equal. Okay. I can indicate things being equal just by drawing lines through them, and I'm going to, right below here, are the forces on this thing balanced or unbalanced, do you think?
Balance.
Balanced. All right. Next situation, okay? Puck is on, and it's between like Michelle and me. Like I pushed it, it's headed towards Michelle. How's it moving? Or it's moving down the hallway, say. Puck on, moving down the hallway. Okay? What can I say about the velocity at this moment? V equals.
First it's increasing and then it's constant.
Yeah, but when I'm looking at like when Cindy was filming it and it was passing right in front of her, what was true about its velocity?
It's constant.
Constant velocity. So let's just write that. Okay. So puck, same as before. Did the interaction with the Earth change?
No.
Earth could care less that the fan is on, right? Doesn't even know. Did the interaction with the floor change? How, Ben? You shook your head, I thought. Did the interaction with the floor change?
Maybe the force pushing the book up more than the Earth is now.
Huh. Let's see one other thing. If I get a piece of paper
Well,
here.
I think that it's still the same, but now you have the air to take into account, which pushes up even more. So that's another force pushing up.
Let's pause here. Write down a one-sentence tweet. This time you're going to read your own tweet. I hope that's okay because I don't have a little piece of. Oh, actually, do have little scraps of paper. So pass these around. Write your tweet. What are you thinking about this? I'm going to get a bigger sheet of paper so I can test an idea. And the question we're kind of considering right now is the floor interacting with the puck? Where's the puck? Oh, it's right over here. Okay.
Are we in a question or?
Let's just say what we're learning. Could be a question. Alright, so here's a piece of paper and here's the puck. Does that show us anything? It just floated right over the piece of paper. Is the table or the floor interacting with the puck? I didn't hear anything loud.
I mean, it's still holding it up. If the table wasn't there, it would fall down.
It would fall. We'll get to that thought in a second. But when the puck is floating across, is it fair to say that the floor is exerting a contact normal force anyhow?
No.
Why not? Because the floor is doing what?
It's in contact with the air from the puck. but not
Yeah,
the
it's not in contact with the puck. If it had been in contact with the puck never would have slid over the paper. Right? Because I'm just able to put a sheet of paper right between them and it doesn't affect it at all. So this interaction's gone. Is there a new thing that's replaced with?
The air.
The air. And what type of force is that?
FM.
Yeah, probably, because there's probably crunching of molecules. What we're talking about. How does the picture look? The Earth hasn't changed its force. Should there be an upward force here? What do you say? We have two interactions. We don't have any more, I don't think. What's the upward force called?
FN of A to P.
A to P. Equal or not equal?
Equal or more.
You want this to be more? I'm going to just write more question mark here. Okay. Balanced or unbalanced? Okay. points out. Andrew.
Well, wouldn't it be balanced because then it would accelerate further and further at a higher velocity?
So you're saying if somehow it's unbalanced, you're thinking its velocity.
Yeah, it would either slow down or speed up, wouldn't it?
Okay. So that's an argument you're making. I don't think we have that established, but that's a possibility. Okay. So let's lay this down. We're not quite sure if these are equal or not. I'm not going to put equal marks on them just yet, because this might be one we need to visit. Okay. Let's switch tweets. And nothing written on the result sheet. So. Okay, start reading, Oscar. Start reading.
We're learning about the interaction between objects and what forces are at work.
We're learning about forces and how they interact on objects.
The floor is not interacting with the puck. I am learning to identify forces in real life experiments.
Velocity remains constant in the midway of its movement. Is it fair to say that there is no friction at all?
Megusa pucks, they're fun. We're learning how the floor is interacting with the puck.
Gravity and friction.
A lot of stuff is happening with this puck, finding out what it is.
We're learning about the different forces being exerted on the awesome sweet puck.
Learning how different forces interact with objects and how to diagram these forces. This is complicated stuff.
We're learning how to map the forces acting on an object.
Quick summary.
I like the one bad
Oh, yeah. Okay, sorry. The floor is not interacting with the puck. I'm learning to identify forces in real life experiments. I love it.
We learned the floor. Okay, so working with air puck. And we just learned floor isn't interacting with the puck when it is on. Is that kind of the summary?
Yeah, it just says the floor is not interacting with the puck.
Okay, then what was the second part?
I'm learning to identify forces in real life experiments.
Oh, my experiments. Oh, -1.
One word.
Yeah,
Word.
one character over. I, comma.
What about is it?
I don't know which one it is.
It's because it used to be text messages. Yeah.
Are we allowed to follow you in those?
Of course. Okay, so this is done. Let's look at one more case. Puck sliding across the floor. No fan. On. Constant velocity or changing velocity? That's this. Constant or changing? Changing velocity. Okay. Puck. Earth. Has that changed at all?
No.
Still the same. Are we interacting with the floor now?
Yeah.
Okay, do we have a normal force with the floor?
Yeah.
Well, we still know we have the normal force, right? There's still crunching of atoms, right? Right? So let's just kind of get those into our free body diagram. Do we need another interaction?
Ooh, sweet. I like this.
Yes.
Oh, nice.
With emergency.
Do we need another interaction?
Yeah.
Frictional force. Between what and what?
Floor.
Floor and the puck. So we have two interactions here. The floor is interacting in two ways. That's because the puck is not only crunching atoms down, what is it doing to atoms?
Pulling them?
Yeah, pulling them along with it in parallel to the floor. We call that shearing. So the puck, as it goes along, is pushing the atoms that way in addition. Okay? So if the puck is moving this way, let's say that the velocity of the puck is this way, which way is the force? That way. Frictional force of the floor on the puck. Those two F's mean different things. Balanced or unbalanced?
Unbalanced.
Unbalanced. There's no way this can be balanced, right? Alright. Maybe one more that we can do.
I'm so good.
We're at time, aren't we?
No.
Yeah, go ahead, Michelle.
I just had a question. Oh, what does that I mean again? Like FNI?
Oh, that's a comma.
That's a comma?
Yeah, sorry. It's just a very big comma. The schedule says, the schedule seems wrong for me. Like, or is this a double or?
Yeah,
is
this
this
is a
double.
Okay, sweetness.
Yeah.
My schedule's like screwed up. Should you want to get rid of physics?
No.
You cut
I don't
me.
want to leave that part.
What? That'd be.
That means there's separation.
Yeah, Ben.
Andrew,
Why?
both of you. Alright, so here's the other experiment I want to try to do. Okay. Kind of think about it. Puck on, but now I'm going to try to pull on the puck. Okay? And instead of like before when Michelle like pushed the puck to me, when was Michelle's force acting on the puck?
When she came in contact with it.
Yeah, so like if she's like just doing a push back for like how long do you think her force is acting? 1 Mississippi? Probably not even that, right? Split second, like 10th of a second. So that's not really like a force that's acting for a long time. I'd like for me to try to make a force act for a long time. Okay? So the way that I'm going to do that, I can't do that by pushing the puck with my hand, right? Okay? That's probably going to be hard for me to do. I'm going to try instead to pull it with a string. I'm going to try to pull it with a string always so that the string is taut. Okay? And we're going to observe how it moves. And in trying to pull it, my goal, I don't think I'm going to be good enough that I can get it so that I'm exerting a constant force. That'd be really nice. But we're just going to settle for me being able to exert any force for an amount of time. Okay? Okay. And this puck is not nearly as good as the other one, but here we go. And I'm trying to pull this in a way, and it's kind of hard to see first of all.
Do you need more string?
No, I think I'm okay with string. The thing is, it's in contact with the floor a little bit more than the other puck. And that's just because there's string stuck in the fan. Okay? And so that makes the fan not work as well, and so it just touches the floor. But you can still kind of see, it's still got some hover puck goodness. Okay? But now the way I'm going to pull this is I want to pull this in such a way that I'm going to try to always make the string tight, and we're going to observe. Is that constant velocity as it came across? No.
No, because you weren't.
Well, the only thing that I was trying to do, like I wasn't trying to pull harder, I was just trying to move in such a way that I kept the string always tight. So that meant if the puck was coming out at me at a certain speed, okay, I had to keep the string tight, but if the puck was going faster, what did I have to do? Move faster. So I wasn't intentionally trying to like make it go faster. I was just trying to hope that the string was the same time. See that difference? All right, let's write that system schema up. I'm kind of running short on room. But this is puck going across the floor. Across floor. Pulled by string. What do we say about the velocity? Not constant, it's changing velocity. Okay. What else have we got? We got the puck. Okay, we've got the earth. They're interacting gravitationally. Is the floor interacting with the puck? No. What is? String. How would we describe that force?
Tension.
Tension force. Any other objects acting with the puck?
The air again?
The area.
Oh, yeah.
Okay, and that's a normal force. And so the diagram that I have, gravitational force of the Earth on the puck, tension force, or let's see, normal force of the air on the puck. And then let's just say for a moment that the velocity is going this way. And let's just say that I was pulling it and I was pulling the string purely horizontally. I wasn't, but let's say that I was. Tension force of the string on the puck. Balanced or unbalanced? Unbalanced. Okay. Is that enough situations? 4 seems like a lot. All right. Is there a pattern?
When there's 2, it's usually balanced, and when there's 3, it's unbalanced.
Okay, that's a thought. All right, here's one more. We won't describe this fully. I could push this in such a way the velocity is constant. Are we in agreement on that?
Yes.
Right? So how does this diagram change when I push it so that the velocity is constant? I add in one more interaction. What's the interaction? Yeah, so it's Mr. Burke, and it's a normal interaction, normal force. And I would add to that a force going which way? The other way. So it would look like this. What do you think about, would it be balanced at that point then?
Yeah, it's equal.
Yeah. So I don't think I can go with Chris's rule where it's like when it's 2, they should be balanced.
Right.
And we still didn't quite settle this. To figure that out, maybe since we have some time, let me get a scale, and you guys think about looking for another pattern. And let's see if we can get the mass of the puck. I need to see if I have a good scale. Very no juice, so I can't get a scale. But I can tell you what the experiment would do. So here's an interesting experiment I could do, and I want you to think about it. I've got a scale, and I put the puck on the scale. Let's get a mass for the puck. What do we think the mass of the puck is? You've held it.
2.
In kilograms. Wait a second. 1 kilogram.
Like 0.5.
That's
Yeah, probably like half a kilogram. Maybe this is kind of a pound. Okay.
2.2 pounds.
Yeah. Okay. So I put this on the scale. I mass it. It's a kilogram. Okay. It's half a kilogram. Okay. When I turn it on, okay, and let's just assume that the scale is such that it'll just sit there with the air, holding the puck up. What will the scale read now?
a little bit heavier.
This is why I wish I had the scale so we could do this.
Yeah.
But give me some thoughts. I want some arguments for why it might go heavier or lighter. What's your argument?
Well, it could go lighter because it's
Down
low
for
on
why-
the scale, I guess, and it could go heavier because the air is acting on
Yeah,
it.
so one argument is it's not sitting on the scale anymore. We've seen I could pass a sheet of paper right underneath it when you touch it. So it could read,
Yeah, but when it passed a sheet of paper, it also pushed it down to the table.
it pushed it down to the table. So it
I
might be
think
that the air is pushing down.
has to be enough to make it go up, so it has to be at least equal to its weight.
So the air is pushing down on the scale. There, again, another awesome thing that I could show you if I had internet is there are pictures of airplanes when they're flying. What's underneath an airplane when it flies? Can another airplane just sit? Can airplanes fly like this? Is that smart?
No.
It's really
Why
it's
not?
like really high pressure.
What's the danger?
Because there is, low
What's pushing up on the, what's holding the airplane up?
Because there's low pressure on top of the wings, and then there's high pressure.
Right, we don't so much have to worry about the pressure difference. That's
But
probably
there's
true,
more
we can
air
figure it out.
below.
But I know that air is pushing up on the airplane. Okay? So the airplane's pushing down on the air.
Yeah.
And so the air is moving down underneath the airplane. And it's really kind of going every which way. You don't want to be flying through that. And you can actually see when airplanes are flying through clouds, and I'll try to remember to post this picture, email me if not. Airplanes leave a signature underneath the clouds. They blow the air out in these weird curly cutters. You So I'm going to go ahead and say the scale, if we were to read this, reads exactly the same. And this is balanced. In fact, this and this are the same, and that and the same. Do we have a pattern now? We're trying to look for a pattern of connecting forces to velocity.
When the forces are balanced, the object is moving. When the forces aren't balanced, the object is
Okay, let's put that idea up. That's a great starter idea. Okay, so balanced forces.
Balanced forces then it's constant velocity.
Okay, I want to get what Madeline said first. Balanced forces equals velocity equals 0. Did that summarize what you were kind of saying first? I think that's a good idea to start with. And I want to contrast that. Sophia, you just said balanced forces
Equal constant velocity.
leads to constant velocity.
Because for this second,
So that's two different, are those ideas the same, first of all? Are those ideas just saying the exact same thing and we should just consider them equal?
No.
No, they're different, they're saying different things. Right? Which idea is supported by which diagram? Is this balanced forces equals velocity of 0? Does this diagram support that in our observation? Definitely. Okay. Does it also support Sophia's question? Yes, it does. Okay. Now here we have puck on moving down the hallway at constant velocity. Doesn't support Madeline's idea. Does it still support Sophia's idea? Yeah. Okay. Puck sliding across the floor, no fan on, changing velocity. Well, we didn't say anything about changing velocity, but what does this imply?
so when it's unbalanced, it has not constant.
Yeah, it implies that unbalanced forces equals changing V. Agreed? Okay. And then that would seem fine. And then when I added my hand and it was balanced, it became constant. And then finally, when the puck was sliding across the floor pulled by its strings, that was unbalanced forces. And what was true about the velocity?
It was changing velocity.
It was changing velocity. Okay? So we can start to say here, which is Sophia's idea? Does that idea seem like it holds up? Yeah, and so maybe we have a general principle here that we can state. If the forces are balanced, okay, we can also think of that as like, what's the total force? Well, if I added up all the forces, what do you think they would add to?
0.
Yeah, the total force equals 0. We will also later call that the net force equals 0. Then, what?
Then the velocity will be constant.
Yeah, then the velocity is constant. The object is at rest. Is that what that means?
No.
No. It just means the velocity won't be changing. Whatever the velocity was before, it will stay that. So it's this idea that Madeline opposed, that's what almost everyone thinks. Like, that's a great starter idea. What's it missing? What's the problem with it? What are we now seeing that this idea doesn't fully capture? Because we look around and I see, like I see the puck or I see your chair, and I'm like, oh, the forces on that must be balanced because it's sitting still. That's almost true.
Well, I don't think it takes into account like the side-to-side forces.
Can you elaborate on that just a little bit?
Well, I don't know. I mean, I guess.
So like that
the
chair,
chair,
right?
It's just being up. Like the floor is pushing up on it, and then the earth's gravity is
Pulling down on it, so it's like that diagram that
Yeah.
forces out.
So then, like when you have things going from side to side, like forces of like tension or like normal forces of pushing, then
Yeah, is there a distinction when we really think about it between being at rest and moving at constant velocity? What if all of a a sudden I put this room on a train, okay, and the train is just moving. And we're having physics class on a train because we're going to New York because there's no power here and it's boring. Okay. Could we, would you be able to tell the difference? The train is like, you can't see out the windows. And it's unlike Amtrak, it's like a really nice,
So it's
smooth
like the
track.
train to the Capitol. and the
Yeah.
games.
I was about to say that.
Yeah, exactly. Okay, it's an awesome, just kind of levitated train. Sweet. Okay? And we're headed to New York. Is anything going to be different? Can you tell, literally, that you're moving?
No, because things inside the
Well,
building.
actually, now the Earth is moving, so
That's true, right? You're sitting on a train. It's actually moving pretty fast. If you were to calculate how fast you're moving right now, because the Earth is rotating, that's pretty fast. You can't tell when you're moving at constant velocity. So you would sit there like, we would look on this train and we'd be like, my drink glass, what's its velocity? 0, right? I can just hold up and I can drink from it. But somebody outside the train, and it's a super fast train, we're going to be in New York in 30 minutes. Somebody outside, how does my drink glass look to them?
Moving really fast.
Yeah, it's moving at
At the
constant
speed of-
velocity right across. Okay. So there's no, the unifying idea is not the speed that we agree on, it's the fact that the velocity is not changing. When would we notice that we're on a train? When it stops, right? Particularly if that train just suddenly came to a stop.
Yeah.
We'd all notice that in bad ways. So this idea is huge. Okay? And we've essentially figured this out. Okay? This idea is also known as Newton's first law. You've probably seen it written other ways. Anybody want to take a stab at how you've had it described before? Anybody ever in middle school heard of Newton's first law?
Was it like, if you exert a force on something, it'll move in a straight line?
Almost, yeah.
Three-dimensional state.
Yeah, it's something like that. So if an object is at rest, it will stay at rest. That was sentence 1. Like if an object, please don't write this down, is in motion, I'm just writing it down so we can look at it. It will what? Stay in motion.
If there aren't any forces.
Yeah, usually then there's an unless acted on or upon by what?
Other forces.
By an
Outside force.
an outside force. Okay. And they're making a real big distinction between being at rest and in motion. And we're not making that distinction anymore. We just say that's velocity constant. Whose idea is simpler? Ours. Newton, I don't think said it this way either. Like Newton said it more.
Well, no, this is like the, sort of like, oh, well, this is sort of easy to say way. Like,
Yeah, absolutely. It's the way that memorizes nicely that you can put in a middle school textbook, but it leaves with kids with big holes in their brains where they think that being at rest is really a different thing than being in motion. When we kind of think it out, we have it this way. Okay. Let's see. So for the rest of this time,
So how do
let's.
we want to put this on the number?
So I would state Newton's first law really in some way like this. If forces are balanced, later on you'll be able to see forces are balanced meaning that force equals 0. Like here's a super simple way of saying it. If, what are we calling the whole model that describes forces when they're balanced? Yeah, we can say BFPM. We just kind of say P is for particle. Okay? Then, what model must be true? CVPM, right?
Oh.
I think that makes sense. I don't think that's the, at first, I don't think you're fully ready to kind of see it distilled that much. And I think that begs a question. If not BFPM, then not CVPM, that's true. So one thing that's true about objects that don't have balanced forces. What's true about their velocities? They change. But it might be interesting, and that's probably a topic for future study, how do they change? Okay. let's work on practice 1 for kind of the rest of the time here. And I think practice 1 involves like, thinking about like a box and kind of rethinking about a box, right? Yeah, I'm gonna see if I can find some cardboard boxes. We're ahead of, I had misplanned the time. So I'll see if I can find boxes to actually test this out. But in the moment, you're using the awesome imaginary box right in front of you. And if I can find one, I'll bring one that you can create a work with.